Welcome to UPSC Study Academy, empowering aspirants and shaping futures.
Today, in the Communication System series, we are looking into the fascinating field of space communication.
What exactly is space communication? Space communication refers to the transmission of data between Earth and spacecraft or between different spacecraft. This includes everything from sending commands to a satellite to receiving images from a Mars rover. But who are the main participants in space communication? The primary participants in space communication are Earth-based control centers and various types of spacecraft. Key Earth-based centers include NASA's Deep Space Network, DSN, which provides critical support for deep space missions. On the spacecraft side, participants include satellites in Earth orbit, interplanetary probes, and space stations such as the International Space Station, ISS. Additionally, communication can occur directly between different spacecraft through inter-satellite links. What kind of electromagnetic frequencies are used in space communication? High-frequency electromagnetic waves are the backbone of space communication. Specifically, the frequencies used include S-band, 2 to 4 GHz. This band is used for telemetry, tracking, and command, TT&C, as well as some scientific data transmission. X-band, 8 to 12 GHz. This band is favored for deep space missions due to its balance between data rate and atmospheric attenuation. It's commonly used for spacecraft telemetry and data downlink. Ka-band, 26.5 to 40 GHz. This band supports very high data rates, making it ideal for missions requiring the transmission of large volumes of data, such as high-resolution imaging or large scientific datasets. It offers greater bandwidth, but can be more susceptible to atmospheric effects like rain fade. But why are these high frequencies chosen for space communication? These frequencies are chosen because they can carry large amounts of data and are less susceptible to interference from the Earth's atmosphere. Higher frequencies, like those in the Ka-band, allow for higher bandwidth, which means more data can be transmitted faster. How exactly does the communication process work? First, a message is encoded into a digital signal. This signal is modulated onto a high-frequency carrier wave, typically in the microwave range, e.g., S-band, X-band, or Ka-band. The modulated signal is transmitted via a high-gain parabolic antenna on Earth. The antenna focuses the signal into a narrow beam to minimize dispersion and maximize signal strength. The high-frequency radio signal travels through space. Despite the vacuum, the signal can be attenuated by factors such as distance, interference from cosmic sources, and the Earth's ionosphere upon departure and re-entry. The spacecraft's antenna, which may also be a high-gain parabolic dish, receives the signal. The antenna must be precisely aimed to maintain a stable link with the transmitting Earth station. The received signal is demodulated to extract the digital message. The spacecraft's onboard systems decode this message to interpret the commands or data. The spacecraft's systems execute any commands received, such as adjusting its orientation, performing scientific measurements, or transmitting data back to Earth. Data collected by the spacecraft, such as telemetry, scientific measurements, or images, is encoded and modulated onto a high-frequency carrier wave. The return signal travels back through space, subject to the same potential interferences and attenuation factors. Earth-based antennas, part of networks like NASA's Deep Space Network, DSN, receive the return signal. These large parabolic dishes are designed to detect and amplify weak signals from deep space. The received signal is demodulated and decoded to extract the data, which is then processed and analyzed by mission control and scientists on Earth. How communication systems fit into space communication. Space communication is crucial for the success of any space mission. It enables scientists and engineers to control spacecraft, monitor their health, receive scientific data, and even conduct live video feeds. Without robust communication systems, managing space missions would be impossible. What kind of information is exchanged during these communications? A wide variety of information is exchanged, including telemetry data, scientific measurements, images, videos, and software updates. Telemetry data includes vital stats about the spacecraft's condition, like its temperature, battery status, and position. How does Earth's atmosphere impact space communication? Earth's atmosphere can absorb and scatter certain frequencies of electromagnetic waves. Infrared radiation is absorbed more in the lower atmosphere, while the ozone layer in the stratosphere absorbs much of the ultraviolet radiation. Moreover, the ionosphere's electrical conductivity can reflect or refract radio waves, especially those at lower frequencies, affecting long-distance communication. What are the roles of NASA networks? NASA relies on three main networks for space communication: the Near-Earth Network, NEN, the Space Network, SN, and the Deep Space Network, DSN. Near-Earth Network, NEN. This network supports missions in low Earth orbit, LEO, by providing communication services for satellites and other spacecraft operating close to Earth. It handles data transmission, tracking, and telemetry for a variety of Earth observation and scientific missions. Space Network, SN. The SN primarily uses the Tracking and Data Relay Satellites, TDRS, to offer continuous communication with spacecraft in higher orbits, such as geostationary and medium Earth orbits. This network ensures near-constant contact with missions like the International Space Station, ISS, and Hubble Space Telescope. Deep Space Network, DSN. Designed for missions beyond Earth orbit, the DSN supports interplanetary spacecraft traveling to destinations like the Moon, Mars, and beyond. It consists of large parabolic antennas located in California, Spain, and Australia, strategically placed to provide continuous coverage and maintain communication links with distant spacecraft across the solar system. Are there any specific methodologies or technologies used to ensure the accuracy and reliability of these communications? There are several methodologies and technologies in place. Error detection and correction codes are used to ensure data integrity. Techniques like modulation and multiplexing are employed to efficiently use the available bandwidth. Ground stations equipped with large parabolic antennas, like those in the Deep Space Network, help in receiving weak signals from distant spacecraft. What challenges are faced in space communication, especially with deep space missions? One of the biggest challenges is the vast distance, which causes significant time delays. For example, it can take over 20 minutes for a signal to travel one way between Earth and Mars. Other challenges include signal attenuation, interference from cosmic sources, and the need for precise aiming of antennas to maintain a stable link. How do engineers overcome these challenges? Engineers use advanced technologies like high-gain antennas to boost signal strength and adaptive coding techniques to improve data integrity. They also design robust communication protocols to manage delays and ensure commands are executed correctly despite the time lag.
Don't forget to like, share, subscribe, and hit the notification bell so you won't miss the next part of our series on communication systems. Thanks for watching.